Okay, everybody. I think it is time to start by my clock. Let's do that because we have a lot of interesting and exciting material today. And I see the chat channel is lighting up with people trying to connect. We'll take a moment shortly to make sure everybody can connect to the exercise platform. So please don't feel rushed right now if you're having minor issues figuring out how to connect to our exercise platform. We'll go over that in a moment. And we're going to do that prior. We're going to give ourselves lots of time before we get into the exercises to do that. So please don't be nervous right now if you're still slightly confused about how to connect to the exercises platform. I'm glad you tried early, but we'll have time to debug any issues you have. So let's jump into the workshop. Welcome. This is one of our Exceed workshops. It's probably it's without question the most popular one we do. This is our first attempt to do it via Zoom instead of a wide area classroom. So we're very used to doing this remotely, but we do have a few more constraints this time around. So bear with us. I don't think we'll have any problems. We are coming to you from the Pittsburgh Supercomputing Center. We're part of the Exceed program sponsored by the NSF to provide you with high performance computing and training and a variety of other things I'll mention briefly as we jump into things. I am John Urbanik. I spend my time working with the tools I'm about to talk to you about over the next couple of days and helping people with their applications and dragging them into the world of HPC. And these days, a lot of that means big data and machine learning. The workshop that you're doing today is, I guess, our second big data one of the year as we churn through the calendar here. Next month, we'll be doing an MPI message passing workshop for those of you that are more interested in the nitty-gritty details of application programming, and then our summer boot camp follows that. But this one, as I said, is our most popular workshop. Our philosophy with these workshops is they're only as long as they should be. So you'll see that this is a pretty compacted agenda because we're not flying people in here to attend these things on a regular basis. We always do these remotely, usually with the wide area classroom. So we've got an agenda that's really not wasteful of any time, but at the same time, we've made a lot of room for hands-on because this is intended for you to leave this workshop having done exercises, being able to use the tools. It is not going to be a couple of days of you listening to buzzwords and jargon from me and not being able to actually use things. We're going to make sure as we go through the content that you can demonstrate competency, at least, beginning competency in everything we talk about. I know you are coming to us from different time zones. I appreciate that. We've hopefully made the schedule as convenient as possible for that. And we very much know that learning is a social process. This is not a MOOC. I'm not just a talking head here. On the other hand, this isn't the wide area classroom format that we usually do. So we don't have the benefit of having a TA standing by you like we normally do. We think this is going to work out just fine, but bear with us as we sort it out. Again, we're used to doing this remotely, but it's not exactly the wide area classroom. So for example, the chat channel could get overwhelmed if our TAs can't keep up with it. So at the moment, I'll suggest you not be too sociable. Sounds like a terrible thing to say. Don't be sociable on the chat channel at the moment while people are trying to get things debugged. Just keep it for urgent things. And as we get into the content more and more, it can be used for, interesting questions and that kind of stuff. Indeed, that is the hope here, is that we have lots and lots of interactivity with you, lots of questions and things like that. The agenda is going to be basically today, we're going to ramp into things. We'll do a little bit of orientation. I'll give you kind of an overview of what big data is about and some of the techniques that we're going to talk about. And then we'll talk briefly about Hadoop. And then we're going to jump into Spark, which will be a big part of today and a little bit of tomorrow even. And that's where we really want to get moving quickly so that we can do some hands-on even before our first break. So you will be doing hands-on by the time we hit our first break, doing real exercises. We're going to talk about Spark for a variety of different applications today. By the time we're done today, I think you'll understand its great power at doing a variety of things. And as a matter of fact, tomorrow we'll start out the day with a very sophisticated machine learning application using Spark. And then we'll morph that eventually into machine learning with TensorFlow, deep learning or neural nets, if you will, which is a very different way of doing these things. Along the way, I'm going to try to present to you a wide array of applications. Maybe some of them will be very near to what your particular interests are at the moment. But it is the guts of essentially a one semester course that we're going to cover in the next 2 days. So it will be fast paced, but we will take breaks to do hands-on and make sure you can use things. And I hope you take advantage of that. So this does sound very ambitious to you because we are covering so much, and indeed it is. We may get, if we get ahead of time with the agenda because there aren't a lot of questions on a particular topic or whatever, I'll take advantage of that so that maybe we have some time later on. The only reason we can even do something this ambitious is because the tools that we're going to introduce you to, Spark and TensorFlow, are very, very powerful and high level, and they give you an awful lot of capability with a couple of lines of this and a couple of lines of that, as you'll see. And so you can really do interesting research level things these days without having to dive down into a very low level. And also, we do this every couple of months. The Big Data Workshop comes around. We've put a lot of people through it. The feedback's been very positive. So we keep pulling it off. Although with the Zoom iteration here, we're taking ourselves a few new challenges on. But I'm confident that we're going to have a successful time here. The biggest potential for things to go awry is that this particular workshop, the Big Data one in particular, is so squeezed because we try to cover so much stuff and squeeze so much in by request. You know, people, every time I try to edit something out, somebody says, oh, that was important to me, or can't you add this? We try to squeeze so much in that sometimes I feel like the hands-on time gets a little bit squeezed. There is a lot of hands-on time here, but never as much as we'd like. So, you know, we think we've fine-tuned it to kind of, you know, hit the middle of the bell curve for people that want more time and people that want more topics, but it still means we're a little bit compressed on the hands-on sessions. The solution for that is for you to take note of things that you'd like to work further on and realize that you have remaining time on the platform, the exercise platform we're going to use today. You've got lots of remaining time on that for the next couple of weeks. So you can go and do these on that platform at any point in time. Plus, everything that we're going to teach you here today is very portable. There's nothing that you're going to learn the next couple of days that you can't do on your laptop. Maybe you'd have to install software there and it might run slower. So you might prefer to use the Bridges platform we're going to use, but there's nothing you can't take back to your own environment and use. However, we're going to let you keep using our environment for the next couple of weeks. So please take advantage of that. So if you feel a little bit squeezed on exercises today, realize that you've got more time to go back and revisit anything that we do. So please do that. And ask questions relentlessly. While you've got myself and the TAs here today and tomorrow, you know, take advantage of that time. Okay, and again, this is something that we do every month. You know, we really, you know, rush through an awful lot of content here, but the feedback that we get indicates that, you know, we do manage to pull it off. So your resources here are our TAs via the chat channel. And again, this is a new adventure for us having all the TAs on one chat channel as opposed to distributed around the various satellite sites. So please be as kind as you can to them. I am happy to take questions from the audience via the chat channel. And what will happen is the TAs will filter the questions that are logistical things that they can help you directly with. So if you have an issue with logging on or a password or something, they'll take care of that directly with you. If you raise a question that's of a technical nature related to the content, the odds are, hey, if you had that question, somebody else is interested in hearing the answer too. And Steve Cunningham will break in and ask the question for you, and I'll answer it to everybody because that's an awful lot of what makes us a classroom instead of just me being a talking head. So I'm delighted to get your technical questions, and I'll be glad to answer them. So please don't hesitate to ask questions. And as we get into more of the technical material today and tomorrow, I expect more questions. Maybe some of the early intro stuff here will be less interesting to ask questions about. The talks are all online. You can find them here if you haven't already. You'll probably find them useful to have by your side as you follow along with me, maybe, although the desktop, you know, is fine. As you do the exercises, almost certainly they're good to refer back to the lecture slides to you know, as a hint to how to do some things. So you'll probably find it helpful to keep the talks open next to you in your browser. One caution there, anytime you're copying code from a web page or a browser in general, it's always a little bit sketchy, you know, as to how things get converted from PDF or whatnot. So for cutting and pasting code, I recommend that you do work from the online directories just to avoid any issues like that might pop up. And I've put copies of all the interesting codes that we'll go through will be in the exercises directory that we'll get to in a moment. So I'd suggest you work, you know, cut and paste from there. And we do have this Exceed YouTube channel now that's become pretty popular. And this lecture will appear there eventually, but the previous iterations of this, which are a little bit out of date compared to this particular talk, gets updated at a furious pace because this field is so rapidly evolving. So the YouTube channel does have the earlier iterations of this, and you can, of course, refer to those if you'd like, or if any of your colleagues couldn't make today's talk and you want to give them some example of what we talked about. I mentioned this Exceed thing to you. For some of you, that may be a new thing. For many of you, you might not have any idea what this organization is. You absolutely should, because Exceed is the NSF's program to provide you, as an American-based researcher, scientist, student, with computing resources when you outgrow what you're using on the desktop. And many of you today are going to learn, and tomorrow are going to learn techniques that will allow you to scale up to massive size. It's the notion of big data. Is it we're going to go from things you might manage on your laptop to data sets that could be petabytes in size. And you certainly aren't going to deal with those on your laptop, or maybe even a departmental resource that you have available to you. And so Exceed exists so that when you outgrow what you have available to you locally in your department, your university, there are resources to make sure that you don't lose your momentum in whatever your research project is. And so exceed.org is a great place to find out about those platforms. The Bridges platform we'll use today is one of those. It's the one in the constellation. It's targeted towards big data analytics, machine learning, appropriately enough. And to get time on one of these platforms beyond the workshop is very simple. To get a startup grant, which gives you 50,000 core hours of compute, which is a substantial amount, you can certainly get an awful lot done, is a 5-minute application process. Here's the official link from the Exceed portal. I find it to be a little bit more confusing than it needs to be. So we've got our own stripped down version of that link, which really does take 5 minutes. It takes about 20 minutes to go through this because you jump through a few hoops that you don't really need to. This is really the streamlined version, but at any rate, the process shouldn't take you more than a few minutes. And then you've got time to continue to work on the exercise platform we're going to use here for the next year. It's a year at a time. And so should you find this platform convenient, and I think you might, because all the software is already loaded and installed and it's got licensed stuff and everything else, then it's easy for you to maintain access to it. Okay, we have a code of conduct for this event, as we do for all Exceed events. If you have any questions or issues, please take advantage of these contacts and do let us know if you have any concerns. We also have a post-event survey that will go out to you. I am always grateful to get the feedback. If you find this workshop beneficial, it's because previous students in previous iterations have given us the feedback that shaped this into what it is. And so please give us your feedback. It's a pretty short form. It's got 1 to 5 rankings, but it also has text boxes in there. And any information you give us in those text boxes, I assure you, I absolutely read every word. So I read every word of feedback that we get, and we use it to shape the next iteration of the workshop. Please do let us know your thoughts, in particular because this is our first Zoom event. So if there are some weaknesses of communication issues or whatever, this is a fantastic place for you to let us become aware of that so that we can accommodate it. Who knows how much longer we'll be Zooming these. So let us know how things are going. And with that, let's jump into the specifics here. In particular, we're going to use a platform called Bridges that I mentioned to you to do our exercises. Now, Bridges is a large, sophisticated, complex platform because it's meant to deal with the many, many different things that people do in machine learning and big data. I hope you'll come to appreciate some of those as we discuss applications over the next couple of days. However, it is not my intention to spend any more time than necessary for you to learn about Bridges or any particular machine. Everything we're going to do in these workshops is very much open standards-based software. Everything we do with Spark, with TensorFlow, with other things like scikit-learn and whatnot that I'll mention along the way will all be very standards-based. You can go back and do this on your laptop. So we want to minimize anything you do that's platform specific. I think we do a pretty good job of that. We'll only have a couple of commands for you to have to use to make your way around Bridges. There are a couple of standard Linux, Unix type commands. Those of you that aren't familiar with the Linux or Unix environment, I think you'll still be fine. Those of you that are, it should seem very natural, normal to you, like any other Linux machine. But at any rate, you don't have to learn about all of these scary looking pieces in this machine here. It's got a lot of capabilities, again, because we'll find as we go along that some projects in big data need a massive amounts of SSDs because they're very IO intensive. Other projects in machine learning want a lot of GPUs because they do stuff on GPUs for reasons we'll get into with neural nets. Other people need very large memory nodes because they're trying to juggle big data sets. And we have 4 terabyte nodes on this machine. We have 12 terabyte nodes on this machine. So we have very large memory nodes on this machine. So we have a lot of pieces, but we don't want to confuse you with that. That is a topic for people that are interested in bridges in particular, not in the general topics of this workshop. So we're going to manage to do everything, all the exercises on just 2 slices of this machine, of its many types of nodes, just the regular memory nodes that we'll use for our big data stuff, and the GPU nodes that we'll use for the deep learning stuff. So with just these 2 node types, we'll be able to do all of our hands-on. And that means you only need to know a couple of commands. On bridges, we've tried to make the machine as interactive as possible. So even though it has all the traditional job systems and queues and whatnot in the background, we're going to be able to avoid all of that. We won't have to touch the batch system. Although batch systems, can be very powerful if you're trying to do research level work on massive data sets and whatnot. But we're going to skip all of that. We're going to let you get away with just using 2 commands: interact to get onto the nodes that we'll use today, and interact-GPU to get onto the GPU nodes for tomorrow. Now, don't start typing anything yet. I'm going to show you the couple things we need to know. Don't start typing yet. We have a little chunk of time carved out when I'm done talking here in a few minutes. You can get on, log on, make sure everything's working. So please don't distract yourselves. Don't jump on just yet. Pay attention instead to the few things you do need to know. So the platform we're going to work on is called Bridges. It's bridges.psc.edu is its destination address. So with any kind of terminal client that you have, PuTTY is probably the most popular one. It's free and pretty straightforward to use. You just need to connect to the machine via SSH, which is the most common way to use a terminal program. So you'll probably be okay with the defaults and just putting in this as a host name, and it will connect you into the machine. You have a password and an account on that machine from the registration process, so you should be using that. And that will allow you to connect directly to the machine. So I saw on the chat channel before we started some people talking about coming in via Exceed and indirect methods or anything else. I'd suggest, unless you're an experienced user, you just use your terminal program at SSH directly to bridges.psc.edu. And by the way, an SSH client might be sitting around, on your laptop or whatever. They're all built into, Macs and whatnot. So use whatever SSH client you're comfortable with. It doesn't have to be PuTTY. So SSHing the machine, and when you do that successfully, you'll find yourself on a login node. The login nodes are pretty obvious because the command prompt should say something like login 1 or login 6. And that is, as the name suggests, where you log into the machine. And it's also a good place to edit and compile codes and do things like that. But it's not where you're going to run. You're going to do extra computing on your own private slice of the supercomputer. So that's a nice thing we provide for the workshops, is you get your own piece of the machine to work on. You won't be sharing it with anybody else. And it's nice for a variety of reasons that we'll appreciate as we get into the exercises. To get that slice of the machine today, all you need to do is type 1 command when you're on the login node called interact. It says basically, give me an interactive piece of the machine. If you type interact, you're going to find yourself on a regular compute node on the machine. You'll know this because your command prompt will change to something like R251 if you're on compute node 251, for example. So do pay a little bit of attention to make sure that you're not trying to do the exercises on a login node and you're on a compute node, because if you do try to do things on a login node, they won't work quite right and will be confusing in odd ways, and it'll just confuse yourself. So please make sure you're on a compute node by the time we get to the exercises, and we'll get to try this in just about 2 or 3 minutes. So bear with me. When you log out, maybe over our break or, overnight or whatever, you'll find yourself having to log back into the login node and then get on the compute node. That's a very straightforward process. So today, again, we're just going to be using interact. And tomorrow, as we shift over to GPUs, we'll use interact-GPU to get onto the GPU nodes. And it should be, again, very straightforward process. And then you've got your own slice of the machine. One other thing we've done to make life as simple as possible is we use modules to manage our software on these machines. And modules, if you're used to a Unix environment, is a wonderful way to make sure that you can load in all of the stuff that comes along with any given package without you having to configure it separately. For those of you that are Anaconda users, you can think of this kind of like this is activating, an environment that's all set up for you in Anaconda, and the packages are all, in place, and there are no dependency issues and all that kind of stuff. Because believe me, with most of these machine learning packages and big data packages, building the software and getting the dependencies ironed out is oftentimes the most frustrating part of the whole process. So just getting something to run, is a pain because there's so many dependencies. The software stacks load, every package they load loads another 20 packages. Those packages have dependencies. So we sorted and ironed all of that out for you. All you need to do is type in module load, and it'll load one of these packages. So today for Spark, for example, as we get into the exercises, I'll come back to this to remind you, if you type module load Spark, boom, the Spark system is set up and ready to go. We can do all our Spark exercises. Tomorrow, we'll actually use a container to run our TensorFlow exercises. And so we can load the Singularity containers to do that. So it's very straightforward, and we'll come back to these as it becomes necessary to do the exercises. So I hope you're not sitting there furiously taking notes on this stuff. We'll come back to it as necessary. We are going to be doing, real coding here. We're going to write some real big data codes and some real TensorFlow codes. And so you're going to need some way to edit things. And back on your own laptop, a lot of you may be comfortable working in a nice IDE environment. Like if you use Anaconda, you might work in Spider to do things. You're welcome to do those things. However, setting them up on bridges, because there's so many configuration options and everything else, we're going to, by default, just assume we're going to do everything in a simple text editing window. So we're going to keep life simple. I appreciate that IDEs can be powerful and can make life a little bit easier to debug codes and to visualize stuff and to load packages. And I'll mention that as we go through some of these packages, how you might normally want to work with them by default. But to keep life simple for everybody coming from different environments and different types of laptops and operating systems, we're doing all our examples here just as text-based, so there's zero confusion about how to take them back and get them to run in your own environment or to move them to some other computing environment. And so because they're text-based exercises, you need a simple text editor. That's all we need. For those of you that are comfortable in Unix environments, you probably know Emacs or VI. For those of you that are not, and I assume that's many of you are not comfortable, you're not, doing C programming on Linux regularly or whatever, that's fine. You're going to be set with the default editor called Nano. Nano is very simple and intuitive and straightforward. If you type Nano, in a file name, you're going to be good to go. It's got some little menus, and it's fine for everything that we need to do to save files and edit files. This is all we need to do to get our exercises done. And we'll try all this out in just a moment here. For our programming language, we needed to pick something. Well, I could have skipped around and done different things for all the different tools, but instead it makes a lot more sense to standardize on something. These days, the most standard language used across many of these tools is Python. Python's become something of the center of mass for a lot of different areas of machine learning and probability statistics modeling, deep learning. So we're going to go with Python. For many of you, that may be a relief because you're Python people by default. For some of you that Python isn't your thing, breathe easy, because we're going to do all the exercises in Python, but I'm not doing them in the most sophisticated Pythonic manner. So those of you that are Python programmers might wonder why here and there I didn't use a list comprehension or do something in a slightly more streamlined manner, because I'm trying to write everything in its most generic pseudocode. So all the exercises are in a fairly generic, again, pseudocode kind of way. So if you're a Java or a C or an R person, you should be fine following along. If you do have any questions, please let us know. But in general, people seem to be very comfortable with the way we've put together our codes, even though they're Python based, even if they're not a Python person. Now we do have one caution here that when you're running and doing the exercises here, some of these packages that we're going to use they're very noisy in the sense that they like to, when you start them up, tell you all kinds of things that are going on in the environment, maybe even throw up a warning that's not really important, but that's the nature of these packages in the complex software stacks that we have in deep learning. And so in any of our other programming workshops, believe me, I don't tolerate so much as a code warning on any of our examples or any of our exercises. Warnings are usually a bad sign in the rigorous programming world. However, in the world of machine learning today, warnings just come with all these software installations. You never stamp them all out. You install your software and get it running, and then you notice it's always giving you a warning that, hey, you don't have a GPU installed on your laptop. And you say, I know that. Well, quit warning me. And it's almost impossible to stamp them out. So we'll have a few warnings pop up here and there in the codes. I'll tell you when they're coming up. Don't freak out if you see those. They're not a sign that something is broken. You'll know when things are broken. It'll be more than warnings. We'll have some flat out errors. Okay, our setup for this workshop today is going to be some one folder that you copy in a moment from a central resource, and then we'll all have the exercises in the same place that we're going to use over the next couple of days. And it'll have code samples and solutions and exercises and everything that you need in that one folder. We're going to copy that over in a moment. And this is where, as I was saying earlier, if you want to cut and paste pieces of that into your own exercise examples, which is always a fun way to go, I'd suggest you do it from these online versions instead of the versions online in your terminal session instead of the PDFs and whatnot that are posted on the web pages. Makes it less error prone, but you can, whatever works for you. Okay, now, as I said, we're going to take a moment and make sure that everything does work here. So we'll take maybe 5 minutes, and get all the boring stuff out of the way so that by the time we get to the exercises, we won't be distracted by this. Plus, it's still, we're about, I guess, not quite an hour away from that first exercise. So any of you that should have a problem, we can do stuff in the background, and you can work with the TAs and get things sorted out, before we get to those exercises. So what we're going to do now is make sure you can all log on. And if you haven't logged on yet, you've got to set an initial password at apr.psc.edu the first time you log on. That was in your instructions that you got when you registered, but you may not have gotten to it yet. So log on to Bridges. Again, you need to SSH to your username at bridges.psc.edu, or however you want to do this via your own terminal programs, PuTTY or whatever. Then when you've logged on, you're going to find yourself in a Unix shell there. And that means we need to do one of the few Unix commands you'll need over the next couple of days, which is copy. You need to copy the exercises folder into your own local directory. The command to do that is CP for copy, -R, that'll recursively copy the whole folder. And the folder you want to copy is ~training/big data. That's a folder in the training directory. And you'll want to copy that to dot. There's a little period here on the end, space dot, and that copies it to your local home directory. When you do that, you will now be good to go with exercises for the next 2 days. Now you want to edit a file to make sure you can do so. So again, fire up, as I said, Emacs or VI. Nano, if the first two aren't familiar to you, fine. Nano will be intuitive and straightforward. Then you want to start an interactive session by typing interact. If you type interact, it'll start up a compute node. You'll see, because it'll change from login to R250 or whatever. That'll be a compute node that you can use for the rest of the afternoon, and again tomorrow, as your own private little slice of Bridges to do exercises. Okay, that is it. Go ahead, give this a shot. Like I said, we'll give it about 5 minutes. If you have questions, let's try to sort them out on the chat channel, and we'll pick up when it looks like most of you are good to go. And if a few of you have some long lingering issue or whatever, fear not, we've got time to sort it out in the background before we do our first hands-on exercise. Okay, I'll take this opportunity. I don't want to distract those of you that are plugging away and are doing fine. Please do your best to ignore me, but I'm going to try to cherry pick some of the questions that I see, common questions I see in the chat channel here, because it's coming fast and furious without our arrays of TAs staked out locally. I see a couple of you have questions about finding the training directory or copying things. Make sure that you're on either the login or the compute node when you try this, which I don't know where else you might be. And if you do this command right here from your home directory, and that's the directory you'll find yourself plopped into when you log in, this command right here should work. And again, it's CP, and then a space, and then a -R, and then a space, and then a ~training, and then a slash, and then big data. Make sure you capitalize the B and the D. Unix is case sensitive. And then a space and a dot. And that should copy it to your home directory. I see somebody saying, how do you access your home directory? Your home directory is where you find yourself when you're logged in. You'll be sitting there. And if you want to see what's in your home directory, the Unix command for that is ls. That's kind of the directory command. So if you type ls, you can see that you're in your home directory, and you should be able to see the big data folder that's there. And later on, as we get into things, you can cd to change directory into the big data folder and whatnot, but that can wait until we get there. What message indicates you have properly started an interactive session? It actually will give you a little blurb saying it's trying to grab resources, and it'll take about 15 seconds or so. But you'll know you're there when the command prompt comes back, and instead of saying login, it'll say R255 or something like that. That's one of the R stands for regular memory node, and it'll tell you you're on one of the regular memory nodes. So that's how you'll know you're back at a Unix command prompt and you're on your own interactive node. How can you copy the folder from Bridges to your local computer? Okay, well, again, I'll make a slight suggestion that you kind of use Bridges if you can, just because all the software will all be on the exact same page. But you're also welcome to take it back, the exercises, to your own machine, and you can do that with any kind of software you have. I suggest WinSCP, for example. If you're on a Windows machine, or I think maybe there are actually versions of that for other platforms as well, is a way to SCP being a generic copy method to copy folders and files. You might want to SCP that back to your own machine. There is also, in the training directory, there's already a zipped up copy of that, a single file. So there's a bigdata.zip sitting in the training directory if you want to grab it all at once. So you can copy bigdata.zip back, or you can copy the whole folder back. But that is I leave it as there's a suggestion in chat, use WinSCP or something like that. So you do need to find on your machine, whatever machine and platform you're on, you need to find out what's a remote file transfer thing that will allow you to do SCP file transfers. That's the easiest way. There are other things like FTP, and you can HTTP gets and things like that, but there's too many ways to do it for me to go through them all. Definitely, if you need to find a client on your platform, like I say, with Windows, I'd suggest WinSCP. It's a free, very common one, very powerful. Drag and drop. If you're on a different platform, on Unix, SCP is built in on the command line, so SCP from any Linux machine. So it's a little research project for you. If that's not answering your question, is Google, how do I remotely copy files on whatever machine you're on? And I see some other suggestions from other users. But again, I'd suggest maybe you don't copy things back to your own local platform to use, because unless you're confident that all the software we're going to be using, we're going to start out with Spark. Unless you have Spark installed on your local machine, it's not going to do you any good to have the data sets and the code samples sitting there. And you can install Spark on your local machine, but it's not something you want to be doing on the fly right now. We'll give it a few more minutes. I do see the questions still coming in here. This is why the wide area classroom format is very effective for us, because we do have our arrays of TAs spread out. So that is a helpful thing. With everybody concentrated here, this can be a bottleneck. There is a reason we put a cutoff on this event of 400 students, because more than that, and we don't have the ability to keep up with all of your questions, both these boring ones getting things going, as well as more interesting ones as we get into content. So that's why we have the cutoff. I'm sorry every month for those of you that can't get in, but you can kind of see the reason for it. With the wide area classroom, 400 people is manageable, and we always have good experience. We're about to find out how well we do with 400 people here today. We didn't want to block anybody out if we didn't need to, so we went with our full normal registration size. But please do have some patience and bear with us. And again, because this isn't our first go round, we have put this preliminary exercise really early, so we can continue to sort things with you in the background before we actually have to start going hands-on. So if it takes Tom and crew a little bit of time to catch up with all of your questions, please don't panic. We're going to get started in another minute or so because we have a lot to cover, but we'll get to everything. We'll get you all going before we have to do the exercises. Okay, we'll get started in just a minute. I'm going to go and reconfigure the chat window so it's even larger and more visible to me before we do that. So. Okay, I'll cherry pick a few more of these questions here as they fly by. Somebody asked about how to exit Nano. If you're in Nano, there should be a little window a menu at the bottom telling you that in that case, Control X is the key to exit. Let's see what else here. Some easy ones. Is there any test file for us to run? There is not at this point in time. I haven't given you a test file to run yet. So the answer is no, there's nothing to test just yet. Okay. Otherwise, it looks like the only issues outstanding are people that do have a few password or access issues, and we will catch up with those in the background as we go here. So let's, for the sake of, well, not for the sake of, for the demands of time, let's go ahead and go ahead. And this next talk is not super technical because, as I said, we've designed things so that as we ramp up and get all these things sorted out in the background, we're not going to deprive anybody of their ability to do exercises or whatever. So this is where we've taken the opportunity to do all of our kind of overview and orientation on some of the big data techniques and where they've come from that we're going to dive into over the next day and a half. So we're going to do a very brief, but I hope useful history of big data and where it comes from and what all this is about. And I think this is important because the term big data and some of the terms, things like machine learning and others, are so loaded, so much hype, so much misappropriation of the words that it's important to kind of give some real definitions and some practical background on what these things are and where they're useful and where they're overhyped and whatnot. So the term big data itself is something that has become so popular to throw at things. Everybody wants to be involved in big data and be a big data scientist. So what does it even mean? And it's a very fuzzy definition, but I like the one that was on Wikipedia, at least a while ago when I captured it. It may have changed now, but I thought it was pretty concise, which is that big data is a broad term for data sets so large or complex, the traditional data processing applications are inadequate. That's a pretty good summary. if you can't do something, on your laptop because the data set's too big and you need to seek out a bigger machine, or the software package you're using just doesn't fit into whatever database you're using, or whatever database you're using can't manage the real-time activity that's going on. Anytime you kind of exceed the boundaries of what your normal applications are capable of, you've strayed into the world of big data. You need tools that are scalable. They can work on, machine room size things, or high performance machines, or supercomputers, or cloud type infrastructures. Once we've strayed into that territory, we're kind of in the world of big data. Now, for a long time in computing, there was no big data because there was only small data. The size of machines and the size of data sets were typically much, much smaller, not that long ago. The notion of working with hundreds of terabytes or petabytes of data was just not something that you could do, let alone a typical researcher being able to do. So when data was only small, we didn't need a lot of fancy techniques to deal with it. A classic amount of small data is grandma's recipe box. If grandma has a recipe box and you wanted to find a tasty appetizer in it, you go to the appetizer section in her box, sorted by appetizers and entrees and desserts, and you grab an appetizer, easy. But even with grandma's small amount of data, if she wanted to use up a bunch of oranges that were about to go bad, how do you find all your orange recipes in a recipe box? There's no obvious way to do that. And so that is where you have to resort to a big data technique, mainly parallel computing on your data. That basically, in grandma's case, means you all gather around the recipe box and dump the recipes out on the table, and you could all help grandma sort through them. Brute force method. It's not sophisticated or elegant algorithm, but it works and allows you to find all the orange recipes and give them back to grandma, right? Well, this technique of using multiple concurrent or parallel resources in order to do searches or sorts or data access is something that we're going to find is very important and is kind of core to most big data techniques today. And it's certainly going to be the basis of Spark, and it's what you're going to leave here with a very good understanding of and a capability to use. So that's an idea that'll keep coming back to us, this notion of working on data in parallel. Sometimes, less sophisticated organization of data works pretty well. You don't have to have fancy databases or really extremely complex organizational schemes, as we'll see, to be in big data or to do impressive things. If you come into my office, it is typically what I like to think of as chronologically or perhaps geologically organized. Things just kind of pile up around there. Matter of fact, at tax time right now, some of you may know what I'm talking about. You're just going through your piles of receipts, and your best organization is things on the bottom of the pile are older than things on the top. And so, it kind of works fine for me. If I need to find all the articles from 2007, I just go start digging around the bottom of the stack, and I can find things from that. However, if I need to find all the articles on fault tolerance, I got a problem. However, if I'm really desperate, I could knock on my colleague's door and drag them in, and they could come over, dig through my shelves with me, dig through the stacks, and help me find all the articles. That would be a pretty desperate situation to drag them into such an ugly task, but it could be done, right? So it's this idea, again, of doing searches in parallel certainly is workable on real-world problems. Now, indexing, as we're seeing here, some kind of indexing scheme, whether it's chronological or better organized, is going to end up determining how well things are going to perform. So if we organize things appropriately, if I were to actually sort my things into folders and files and be better organized, then maybe it would be easy for me to find all the articles on fault tolerance. But that's just not practical. Well, it's not going to happen for me. And as we'll find out when we get into big data sets, it's not practical a lot of times to organize things so perfectly. You just can't do that. It's nice to live in a world like libraries have been, where over the centuries, they developed these very nice schemes for organizing the data. So if you go to a library and you want all the books on modern physics, that happens to be Dewey Decimal section 539, and we can get all of those books. If you want to find the books by Wheeler in that section, you can go to the card catalog, and it will point you to all of the books by Wheeler. However, even these well thought out, labor intensive schemes will fail, because what if you want to find a book where he isn't the first author? Now, all of a sudden, the card catalog doesn't have that organizational scheme, and we're in trouble. We resort to recruiting all the librarians and going up and down the shelves in that section and trying to find all the books with him as an author. So the idea that your organizational scheme is going to be perfect for all cases is something that we've kind of given up in the modern era of big data and very agile data organization. So we'll see the alternatives that allow us to kind of give up on that. But first of all, it's important to understand where big data kind of comes from. Why our data is so overwhelming if you want to have understanding of the trend right now and in the future. Because at one point in time, data was very expensive. Here's what 5 megabytes of data looked like in 1956. And it cost $250,000 in 1956 dollars for this 5 megabytes of data. So it was very pricey, and people didn't just store everything that came along. You really thought about what you wanted to save. That's very different from today's approach. Today's approach to data is don't throw anything out because mining it later on may have value. So today you can grab your 8 terabyte drive for $100 on Amazon. So storage is cheap. So now why not keep everything? And companies out there have taught us to keep everything for monetary and commercialization reasons. Facebook and Yelp and Twitter and YouTube. Those guys grab all your data all the time so that they can analyze it in different ways and monetize it, or as a way that you might think of it, or make your life better is the way they probably phrase it, more convenient. But at any rate, keeping all the data has become a thing. Now that's equally true in the scientific world for perhaps nobler reasons, which is where we have instruments today coming online that generate ridiculous amounts of data on an ongoing basis. In the astronomical world, we have sky surveys that are constantly scanning the skies and bringing in new high-resolution data all the time. We have genome sequencers that are out there that are reading genomes on the population at large. It wasn't that long ago, the turn of the century, basically, when the human genome was first sequenced. It was a painstaking process that took years. Now we have genome sequencers that do that in a matter of days, and they do it concurrently on hundreds of people. And so getting your own genome sequenced is no big deal. And so that kind of data is constantly being generated and spit out, and genome sequencing is a huge area in science. It's got great applications, including to our current crisis right now. Other things you might not think of as traditional, as big data applications have wandered that realm, including very old things like archives that are out there, paper archives, collections of stuff. They're digitizing all of this stuff and making it available so that a researcher, instead of having to travel the world and go through dusty tomes, can now sit at home and do comparisons across texts and find, in some cases, very interesting and novel connections between data across historical periods or across geographical areas at the same historical period, because they're collating things that we're never, again, able to do except in a painstaking manual process in person before. We have things like weather satellites up there generating climate and weather data on a regular basis. So there's no shortage. I could talk for hours about big data sets that we just have on bridges and science we just have going on bridges all the time. As a matter of fact, today you're competing with, if things are a little bit slow on bridges, it's because we are running COVID simulations with a group originally at the CDC, now DOE based, that are doing emergency urgent runs with COVID because that is a big data application. And so, they're trying to model the entire population, essentially. So these kind of things have become almost normal. So data got very big, and data sets, started to become terabytes in size routinely. As a matter of fact, people for a while tried to define big data as data that's bigger than some limit. And for some reason, somebody decided that a Library of Congress is a good thing to compare data sets to. How many libraries of Congress is that data? And somebody somewhere else in a silly estimate decided the Library of Congress is about 10 terabytes of data. That was never a good estimate to begin with. It's a silly notion at any rate. But the notion that data is just judged on its size is naive. It's something that you quickly become disabused of when you get into big data. So data can be big, fall into the big data realm and need special ways of handling it because it is just a lot of bytes. So that is one sense of biggish. So we do have things, for example, on bridges. We've got the 1,000 Genomes Project that's also hosted on AWS. That's 260 terabytes. Common Crawl, which is a way of indexing the whole web, that's also hosted on bridges. That could be 300, 800 terabytes, depending on how you index it. So these are big just because there are a lot of bytes. That's true. But there are also other ways of looking at big. We have throughput. The amount of data that you're trying to capture and maybe analyze and distill down because you can't store it all, it's too enormous, is something that makes something a particular big data applications becoming very common for a lot of projects now to find themselves in that situation. So the square kilometer array is maybe the most awesome one, awesome in a scary sense maybe, that I know of. That's a project that's being deployed and built right now that will eventually, in its full deployment, do over an exabyte of raw data per day. When they compress that down, which compressing it alone is going to require big data techniques to compress it as fast as it comes in, it'll be 10 petabytes of data that they want to store per day in a full instrument. So that's obviously a big data application because of its throughput more than anything else. But these days, it's quite common to find lots and lots of Internet of Things based projects too, where things are coming in streaming from the most common Internet thing might be your phone. We're tracking people from their locations or what they're doing on their phone. But there are lots of other Internet devices. If you wear a Fitbit, for example, that's endlessly streaming things back to servers somewhere to analyze things. So this Internet of Things idea, and scientific instruments, for example, are being deployed, buoys in the ocean to measure ocean conditions. Those kind of things are being deployed routinely, and they're all streaming, and that means something needs to grab that data and process it, at least preliminary wise, to try to compress it down and filter it to some degree. And then after it's stored, it's an enormous amount of data that you've got to handle to do anything useful with. So this is a throughput idea is an important part of big data. And this last one here is kind of the third component of big data that is overlooked by a lot of people, which is the complexity of the way you store your data. Can be very much something that you can't deal with in any traditional, normal laptop level data processing sense. I'll give you an example. This is one we're going to dive deeply into with our exercises. But here, just to give us a taste of it, is GDAL, for example, which is a global database events, language, and tone. You can think of it almost as kind of a newsworthy events database that is soon to be hosted on Bridges. It's currently a Google database that people grab pieces of. It's only about 2.5 terabytes of data per year of that database that you look through, but it's trying to capture newsworthy events, and that's a very ambiguous term. And so if I said to you, what are the characteristics of a newsworthy event, we'd probably all immediately say, well, the date is one thing, the location's another, maybe the country, and we'd all come up with a handful of fields that would characterize an event. But it turns out that, over time, as more and more real newsworthy events need to be classified, they've grown that up to 59 fields. We would certainly, none of us, come up with all 59 of those fields to start with. So it's an example of how the complexity grows as the data set grows, as an experience, with the real world application grows. So this is complexity. And as a matter of fact, I think of these as the 3 V's of big data: volume, velocity, and variety. These are the things that really will push you into the realm of having to use Spark or potentially other techniques to handle the data. Okay, well, why can't our classic good old SQL relational database techniques that were good enough for decades, why can't they keep up with stuff? And there are, many common SQL databases, and they're still in common use. And you interact with them, via user applications all the time. They're the backing stores for lots of data. So these are very common and useful types of databases. And they were basically, the idea is you put things in tables. And tables can relate to each other in certain ways, but all of your data is in, well-organized tables. Well, why wasn't that fashionable for a while? Why was there this no SQL movement that kind of kicked off big data for a long time? And the reasons are, well, they're multiple, but one of the reasons is that your schemas, or your organizational schemes, basically, were kind of set in stone. Anybody that designs a relational database pretty much comes in hoping that they capture almost all of that structure in advance. On day one, they lay out the tables, and they try to get it all right. Now, everybody acknowledges that, yeah, you might have to tweak the tables later on, add a field here or something, but you certainly hope that you capture most of it, because reorganizing and refactoring the database is a painful and expensive thing for a big table-oriented database. So the idea that you would just casually come in one morning and say, hey, how about we add in, if you're Fitbit people, how about we add in heartbeats, logs to the database? It's not the kind of thing you want to do with the traditional database, but you'd like to be able to. But the schemas are kind of set. So that's one reason why SQL wasn't, the answer coming out of the gate for when data started to grow in these large, quickly evolving chunks. Also, queries across multiple indices and multiple tables can get very expensive. Anybody that actually works, a database administrator that works with these databases, will tell you that if you don't have your key structure set up right and you issue the wrong type of query, it can go from a typical query maybe taking a fraction of a second to all of a sudden it takes minutes or hours, because it's just digging in some very inefficient way back and forth across the tables, trying to do a join, something like that. So there are lots of ways that these databases can perform badly. Sharding, or breaking up these things into pieces, maybe for redundancy or backing them up or distributing them geographically across different data centers, is not quite so trivial either. You got to think about where you want things to be spread out, how should tables be broken up. It's not a trivial thing to do. But this last one here is actually the most important one. And that is that caching is tough when you've got a lot of guarantees and robustness and checks in your data, which is awesome. If you're a bank, you want your database to be super reliable. I want to know if I go to my bank and I check my balance and I check it a minute later, I want it to be the same balance. I don't want it to go up and down by even a couple of pennies. That would make me kind of uncomfortable, right? Whereas in many web applications, you're perfectly fine with that. If I do a Google search right now on some term on, say, caching, and 2 minutes later, I do another Google search. If that first page has a couple different results, I don't freak out, right? I mean, that's kind of the world that we're used to with a lot of things, is that things don't have to be all repeatable. But again, with your bank, you want them to be repeatable. And so over the years, SQL type databases have developed some very formal requirements, ACID guarantees, that basically put together guarantee you that things are extremely well understood in their reproducibility and their failure modes. And so that even though I'm accessing my bank account with my ATM card, at some ATM withdrawing cash, and somebody else is using a debit card for the same account somewhere in Argentina, buying a box of cookies, and my bank just decided that's a good time to update my interest that I'm earning on my account for the month. Even though all those things are happening at once, there's zero chance that they're going to step on each other and cause some invalid state. Everything is always perfectly understood. And even if the power goes out on that ATM or maybe even the server that's recording things, it's still journaled in such a way that they can reproduce stuff. Those guarantees are very expensive in terms of the kind of optimizations that they prevent. In particular, caching, or keeping local little copies. Caching is central to almost all modern computing performance issues, not just in big data. Just to make your laptop run well, it's got all these caches in it. It's got first level and second level caches on the processor, memory, it's got caches for the hard drive. Everything's got caches everywhere. And those caches are basically to keep copies, small copies of chunks of data that are most recently used, is probably the most common way to use a cache. Those caches are wonderful for performance. They're essential in modern computing, but they really mess with the idea of having one master copy. And so SQL databases with their guarantees are just slow when working with huge chunks of data where maybe we don't care to be quite as precise as a bank. And so that is where we can move on to simpler schemes that have a lot less behind them. And the most simple scheme you can possibly have, and one we'll find ourselves coming back to both today and tomorrow, and in your future in big data, is a key value store. This is basically the simplest database you can possibly have. And a key value store is where you have nothing more than a key, a string of characters, is the best way to think of it. Don't even think of it as a number or some well-organized thing. A string of characters that gives you the key to some chunk of data, some pile of bytes. So this is a key value store. So if we say get foo, the database says foo is the key, and I will return you a pile of bytes, which happens to be var, and that's all I'm responsible for as a database. It doesn't do any more organization than that. So it's very agile. Certainly, we don't have to set anything up. We just start throwing data database and give everything a key so we can pull it back out. That's all of our organization. It's scalable. If we run out of space, we can just buy more disks and stack them into this pile of bytes. The only organizational optimization we need is a good hash scheme. In other words, an algorithm that gets us from our key to find things in the database would be good, but that's a very mature algorithm space. People understand how to do that. If we want to do sharding and backup, it could be pretty simple. We might just reproduce hard drives and have multiple copies of them, as long as our hash key could find them. That's why key value stores are widely used for lots and lots of things, like session information on web pages, for example, is usually a simple key value store. Your shopping cart. So if you're a shopping cart on some web page somewhere, piling stuff into your cart, it's probably just a simple key value store of your cart at that time, which is also a nice illustration of the fact that keys are not necessarily, again, simple numbers. That's something that takes a little while to get out of your head. A key in a key value store can have a lot of structure to the key itself. So this might be your key on an online web page where you're using it to keep track of your cart. It might have a key that looks like this cart and then a username and then a timestamp for that user. And so when your key actually has a lot of information embedded in it, and that's typical. But a key value store, that's it. So I say get this, it goes and says for this key, whatever is embedded in it, I know where to go find a chunk of bytes, which should be that person's shopping cart. Okay, well, that sounds simple and straightforward, but how does that solve our problems here of that our SQL databases have? Because we're giving up all these ACID transaction guarantees, but doesn't having no organization cost us something? Because we got to dig through all these bytes to find the right thing. And the answer is yes, it does. It's not as well organized or indexed. It's not the equivalent of the card catalog at the library. But if you remember these librarians that helped us out when the card catalog failed us, well, today, this is what they look like. They look like a data center. And a data center has millions, at least, of cores in that data center to chug through all of its disk drives and find data. So when I do say, find me that shopping cart, even if there's no other organizational scheme, no timestamps or anything else to go by or order to the queue, it can go and dig through all the data in parallel and find that for me. So this idea of parallel computing of big data centers, it's what makes key value stores and simple-minded agile data schemes possible. Now, as soon as everybody became convinced that the future was just key value stores, it became clear that, having some organization on your data is kind of nice, because it would be nice if I could actually do searches on my data that were a little bit more sensible than just give me a pile of bytes and it's up to me to dig through them and see what organization's in there. Instead, I might like to issue a search like, get me all the plants in the database that are of type DAISY, which means I need some kind of database that's capable of organizing its data and doing searches in those piles of data. It has some structure to the data. And this is where document stores come into play. Document stores came along and said, okay, let's have some kind of organizational scheme in our data. We're not going to be very strict about it. It can be these very loose schemes like just some XML or some JSON file, right? Which just could be anything. You can put anything in there, but at least it's got enough organization to say, look through that JSON. Let's see if there's a field in there that says what the plant type is and if the plant type's DAISY. So just by saying that I've got any generic organizational scheme out there, and again, the most common ones are XML or JSON or binary JSON, just by having those out there, you can start to do some kind of searches that are a little bit more sensible. And that's very helpful because then your parallel librarians don't just bring you back a pile of bytes and say, hey, you look through this. Now they can be a little bit smarter and say, I only brought you back all the records where plant is equal to DAISY. And so document stores became quite popular. Well, as people, started to use document stores, and recognizing that data has some structure that's useful and that abandoning SQL completely is kind of maybe not a sensible thing to do, wide column stores became an option. It became more and more popular. And a wide column store says, well, let's introduce some kind of table structure to our data, because at the end of the day, that's oftentimes a very useful structure to have a record with fields. So let's kind of maybe have some fields in our data, but let's not have to commit to them in advance or even at any point in time. Let's be very flexible about what our fields are, so that in a wide column store, we can still do these SQL kind of searches. So this is what some SQL code might look like, or it looks an awful lot like SQL code, but it works on something that's not nearly as structured as a table database. Instead, a wide column store says that user Joe's record here might have an email and a web page, but Julia only has an email and Mac only has a phone. And so we find that we can be very flexible about what fields we have for any given record, but we still have this kind of nice ability to look through things like it is an SQL table almost. I think of this as a 2D key value store. So basically you give it a key to find the record, and then you give it another key to find the field that you want. So it's very flexible in that sense. And these different databases and schemes all have different ways that they collect the data and organize it. So for performance reasons, it can be, maybe you write more than you read. Maybe you almost never read, things like that. So there's different ways of configuring and having different databases to have different priorities. But the idea with the wide column store is that every record can be different. Okay, what's the last form of record that we'll find ourselves looking at and using is one that seems very exotic until you think about it a little bit, which is a graph store. Graph stores store appropriate enough graphs. And that's great for things like the semantic web. Anytime you're trying to analyze things on the web's a big graph if you think about it, one thing linked to the next thing. So that's semantic web searches and crawlers and things based on the web are often involved with graph databases. But it's also, as I say somewhat sarcastically here, it's also great for graphs because people seem to be very comfortable with graphs and computer algorithms. Your first programming course very often involves somebody teaching you how to do maybe a linked list or at least a data structures course or something. So it's not foreign to programmers to deal with graphs. A linked list is a graph. One piece of data is linked to the next. And there are lots of problems that you think of as graphs if you're trying to find a traveling salesman problem and lots of problems in math or graphs. People are comfortable with graphs. It's only when you talk about a graph database that they get uncomfortable and think that that's a really, again, exotic, different thing. And part of that is because there are some things about graph databases that are a little bit tricky to implement. It can be hard to visualize data organized in a graphical way. That simple graph I just had with 5 nodes earlier is easy, but how about the real world where data at scale looks more like this? That gets to start to look like a rat's nest and very difficult to understand the relationship data. Serialization, or in other words, writing the thing out as a bunch of bytes to disk somewhere to store it, can be difficult. How do I organize things when there are graphs? And queries are certainly different. The kind of questions you can ask of a graph database are actually different than the kind of questions you can ask of an SQL database. Like the 6 degrees of Kevin Bacon thing, where you're trying to relate friends of friends or associates of associates. Those are questions that don't make sense with SQL data. For SQL database to say, how many friends have 3 friends that have 3 friends is a weird thing to ask. It's really not easy to do. SQL data or graph databases, that's exactly the kind of questions that you ask. Relationships. So these things are different, and that's what makes people somewhat intimidated. But because the graph algorithms are so generally useful and so common in computing, they're important things to understand. So query languages that look kind of like SQL have popped up. So this looks kind of like a little bit like SQL, but you can ask different types of questions than you can of SQL. You can ask questions about relationships. The first one was a standard World Wide Web standard called Sparkle. It assumed everything was in a triple form, graph, subject, object, verb kind of form, which kind of makes sense for graphs. Does make sense for graphs, but it was somewhat limited. It couldn't deal with things like the weight, the strength of connections between things, which is useful. It couldn't deal with subgraphs, saying something's a separate subgraph. So the limitations led people to develop some other things, which for a while were proprietary. Cypher, which was Neo4j only for a long while, was proprietary and had some nice extensions to it, which are now kind of rolling their way back into Sparkle. But Cypher is now no longer Neo4j only. It's now an open standard too. And so these SQL languages are useful if you're dealing with graph problems because they're all the infrastructure and framework out there for you to use. And if you don't think, and again, if you think that they're exotic and rarely used, well, think again, because some of the biggest pieces of web infrastructure you use all the time, like the engines behind your series and your queryable web interfaces are usually graph-based. So Microsoft Bing Knowledge Graph, it has 2 billion primary entries and 55 billion facts when last I updated the site. Facebook, 50 million primary entries, 500 million assertions. Google Knowledge Graph. So these are all things that are used by very common popular applications and make them possible. And there's certainly big data at that scale. Okay, so this leads us on to our next topic, which is Hadoop and Spark, which we're going to talk about and start using. What kind of databases are they? The answer is they are not databases. Instead, they are frameworks for databases. Okay, people say that all the time, and that can be very frustrating when somebody just gives you an answer like a framework for data. Like that answers the question. What does a framework for a database mean? Well, we're going to find out it has a very actual real world definition, and that it gives you those parallel librarians that were those army of librarians to search with. That's what Hadoop and Spark give you. That's what the framework really means. It means that you can issue a command from maybe any of these database formats that we've talked about previously. It can implement any of those databases. But when it comes time to do one of those searches or to add data or do whatever, it has hidden behind the curtains for you an army of parallel librarians to go search through stuff. The army is, again, a data center, and it's a bunch of cores, a bunch of computing cores on a bunch of blades in the machine room. They search through a bunch of disk drives, but that's what the framework means. Now, Hadoop was the first one because as big data came along, people recognized the need for it. Hadoop came along and said, here's a way to do it. But it was the first one Its mother was necessity, the need for it. So today we tend to ridicule it because it's clunky, as we'll see. It's clunky and primitive, and Spark is much nicer, higher level way to do things. But it was the first, and it left behind a lot of useful pieces that other things have built upon. So I draw it here as kind of the Stonehenge of database frameworks because it was the first. Whereas Spark is kind of newer, but I don't want to fool ourselves and be embarrassed. 10 years from now, Spark is still where maybe the pyramids of database infrastructure. It's the latest and greatest, but it's certainly not the final word. But it's been around. It's gained a lot of success now. It's the reason we're going to use it because Spark is much more advanced than Hadoop. Although, funnily enough, one of the latest things in Spark is, my mouse is, there we go, is the fact that it has now rolled in nice SQL-looking commands in the form of data frames. So what's old is new here. But at any rate, it is a framework that will allow us to issue nice single-line commands that in reality go and get executed by a bunch of stuff in parallel. So that's what's really going on behind the scenes. Now, the pieces that Hadoop left behind are really important because they're what we build on with Spark and other things as well. So we have all these kind of different little plugins, the file system, schedulers and interfaces and file formats that Hadoop developed that we'll find ourselves leveraging and building on as we use Spark. So, and lots more besides that. So let's go ahead and quickly go over Hadoop because it is, as I've said, it's kind of, to be honest, in some sense, obsolete. Today, you wouldn't want to build an application from scratch on Hadoop. Nobody does that. But on the other hand, people do want to have an understanding of what it's about. So this talk keeps getting more and more compressed every time we give it. And Brian typically gives it, but for the sake of our first Zoom attempt here and keeping things as streamlined as possible, I'm going to give it, knowing that Brian is online here, happy to answer questions, not just here in real time, but also over the next day and a half. If you have a question, if you're somebody that is interested in Hadoop, you've either got a legacy Hadoop application, you've got Hadoop components in whatever you're doing now, Brian is an expert and can answer your questions, but I'm going to give you a very quick overview of it. And as I said, this talk keeps getting more and more compressed because Hadoop is more and more deprecated in some sense, replaced by Spark. So what is Hadoop? Well, it's this platform that gives us behind the scenes all this parallel capability. It's a file system that works in conjunction with that. We need a parallel distributed file system. And it's also a stuffed elephant, as Brian likes to point out, because it was named after the developer's daughter's toy, elephant, Hadoop. So what does Hadoop do? Well, it distributes files around and replicates them so that automatically for you. So you're just storing things in this Hadoop file system, and it worries about the responsibility of spreading them out amongst all of the disk drives and nodes so that things can be done in parallel. You don't have to worry about the details. And it tries to keep them close to the CPU so that the CPU, which has to do the searching and sorting, can do it as efficiently as possible. And then when it's time to actually do that search, when it's time for you to say, find me all the plants that are of type Daisy, that it will take care of that. But Hadoop's maybe, it's not its weakness, but it's the straitjacket that we have to use with Hadoop is that it forces us into this paradigm called map reduce. It's a very powerful and flexible paradigm, but it's not always the most natural one. And I don't want to think about that if I just want all the plants that are equal to Daisy. I don't want to think about that in terms of map reduce. Hadoop forces us to do that. And that's why it's a little bit more a lot more painful than Spark, which will allow us just to say, oh, just give me back all the plants that are equal to Daisy. So we need to do these things in a very specific way with Hadoop. So let me bring my laser pointer here. So Hadoop is saying the data has to be mapped in. So the map function basically says, and you can think of this in terms of a key value store. I won't force us to do that because we're not going to spend a lot of time here thinking in a Hadoop-y kind of way. So if we were doing a class on Hadoop for a couple hours, we'd have to realize everything's going to be thought of as kind of key values. And we map, the map function takes one key value to another key value and then reduce, sorts them all down. But we won't worry about that because Spark's going to make all this stuff much more intuitive and easy. Instead, we'll just say that with Hadoop, you take your data, which is parallel and distributed and large, you do some maps on the data to say, how do I transform the data into the form that I'm now ready to filter down? And then we do our reduce, which filters the data down. So this may be plants equal to daisy. This maybe goes through all the records and makes sure that plant equal to daisy is exposed in some way. And then this reduce only brings back the ones for plants equal to daisy. And then we get our results. And that's the way and the only way that Hadoop operates. So it forces us to address every problem in that map reduce manner, which again is oftentimes not intuitive. It's usually efficient, but it's not intuitive for a lot of problems. So the file system behind Hadoop, though, does remain very useful today. And a lot of Spark systems, for example, are built on HDFS, Hadoop file system, because it does provide some things that didn't go obsolete, like replication and fail-safe replication of things. And it is, however, a write once, read many oriented file system. The idea with Hadoop is that you're storing a lot of data there to analyze later. You're not rewriting it or reorganizing it. So if you want to go back and change a record, you basically have to rewrite the whole pile of data over top and abandon the old data. So it's really the idea is that we're storing data. We're analyzing it, but we're not really going back and we're not changing records like in your very well organized, say, inventory database, where you just want to go back and add 5 to the number of fishing lures that you have. That's not the idea. So instead, Hadoop is meant for massive just piles of data that you keep accumulating and keep analyzing. The file system is actually built on top of a regular file system. So really, the Hadoop file system makes it look like a single file system to you, but it's built on top of some other hard drives scattered around that think that they're normal file systems underneath this thing, because they are. And it collects them all together and worries about distributing the data and making them look like a single unified file system for you. It's one of the powerful things that Hadoop does. That hasn't become obsolete. That's still a useful thing. It has a resource negotiator on top of it to control and schedule all this stuff, because this stuff's all running on computers that are distributed around. So it needs to worry about what gets to run where and how to spread things around and control access. And that's a piece of it. So the Yarn Resource Manager basically says, you as the user are running these clients things, a database request up in front, and it worries about how to go and run all the cores that need to do the search and find the data and return the result to you. So using Hadoop amounts to you load data into the Hadoop file system. So you can't run this out of your normal drive. You run this out of, it looks like it just looks like a differently mounted file system, but it's not your local normal drive. Instead, you move things into the file system with its own special file system commands. Once the data is in that Hadoop file system, you can run a program. The native way of doing it originally was Java. So, there's definitely a little bit of preference giving to Java, but we'll see you can do it with other programming languages as well. And it works in the streaming format. So it likes to work like things, if you're a Unix person, like things that are piped into each other into a stream. So you send it the job and it it does a mapper, and then it does a reduce, and things are kind of piped along until the data comes out the end. Again, we don't need to go into a lot of the details. I'll give you a quick example of it because we're not going to find ourselves using it. And you submit the thing as an actual job. So again, there's a lot of overhead to doing these kind of things, mental overhead, that is. So here are the file system commands, are things like HDFS, put, and get. They look almost like FTP commands, file transfer commands. For any of you that are used to file transfers, that's what they were built to look like. So we actually transfer files into the Hadoop file system, and we can do operations there, but they're, it's definitely a separate file system. So we could put the file systems into training data sets there and do some things. There's some permission things to worry about. So Brian's always got a lot of caveats and warnings here to make the stuff work correctly, because you do have to worry about it. It doesn't do the most graceful and obvious things, like if you write over an existing file and whatnot, it can be a little bit confusing and unfriendly. You get used to those if you're a regular Hadoop user, but for somebody new to it, it's not as friendly as you might think it could be. So you write a program that does the mapper and reducer scripts. You write a couple of scripts. Those scripts read from their standard in and standard out. You could use built-in Unix utilities. You could write in any language like Python, for example. But Java is kind of the way you'll find most of the examples and everything. You set things up as jars and they run. And the idea is, here we have some sample jobs that you can run through if you're really interested in this, which is that you could use cat, the Unix cat command, which basically just dumps out a file. So if you want to have a file and you say cat on it, it'll concatenate it by itself. It'll just dump the file out for you. And you could use word count. The Unix word count command is a way of reducing the data down. So if we have a file, a bunch of files, we want to actually just find out how many words are in them. That's reducing the data in some sense. Here's the way you would actually run that. And you can see there's a lot going on here. You got to have your input and output stream set up to make sure that your mapper and your reducer specify these commands. So there's stuff going on here. It's not super friendly. It's going to be a lot easier to do in Spark. And that's the reason we won't spend a lot of time on it right here. But again, you should know what Hadoop is because it'll keep coming up. It's dominated for so long the space of big data. And again, a lot of the pieces are still sitting around being used. So here's a way to do with Python scripts. If you cared, you could run these scripts as the mappers and reducers, and you put the input and the output into the right things, so things are piped along correctly, and you end up with the correct result. So if you really care about Hadoop, go back, stare at this slide, and you can ask questions about it of me in this case, or Brian if it's more in-depth things. Here's a Java example to do the same thing, and you get the output back in Hadoop file system, so you got to go back and look for it there. And again, these things are inconvenient. They're fine if you're a full-time programmer and setting up all these scripts and everything else in batch jobs in a big environment. You can deal with all that overhead. As somebody that just wants to read some data and do some analysis, that's a pain. So that's why we're not spending more time on it. But Brian's available as a TA to answer your questions. And let's see, I just glanced over at the chat here quickly. So Brian will probably answer, is there a sample data set in the material? Yeah, we just copied. No, the data set for this is still left back in the training directory. Brian can point you. I didn't want to muddy up our data sets with this, but it's back in that training directory. Brian can point you to that since somebody's actually interested in going to Hadoop stuff. So for those of you who are interested in Hadoop, again, Brian's around to answer your questions. But for the rest of you that don't have a pre-existing Hadoop interest, I will suggest that you pretty much forget about it, because what you're about to learn, what we're going to do right now, and what we're going to get into with real exercises, is much more powerful, simpler, and there's a reason it's kind of superseded Hadoop everywhere. So nobody's starting a project today with Hadoop. Instead, the most popular option, it's the reason we've chosen it here, is Spark. Because Spark went and took all of the good things about Hadoop and addressed its shortcomings. Some of the shortcomings were the fact that Hadoop pretty much wants to operate out of disk, because when Hadoop was developed, disk was becoming cheap, but RAM was still pretty expensive. And over the past 15 years, that has really changed to where today RAM is very cheap. RAM is something, if you build a machine, a computer for your own personal use, you go, why not get 32 gigabytes? Just why not? Why not 64 gigabytes? If you're a gamer or something, why not? On bridges, we have nodes that have 12 terabytes of data on a single node. So RAM became a lot cheaper. And of course, it's higher performance to have your data sitting in RAM if it can. So Spark tries to use RAM as much as possible. It will move as much of your data into RAM automatically for you from disk as possible. So if you're accessing your data sets and they're originally sitting on disk, as they get accessed and move into RAM, and as your analyses generate results, they stay in RAM. So Spark uses RAM in a really smart way. Hadoop didn't really have any of that kind of smarts built in. It also was built from the ground up to say, hey, let's actually make this easy to use and not just something for full-time professionals to build painstaking scripts out of. And so it's first-class citizens or Python Scala. It's written in Scala. The developers, obviously Scala enthusiasts, and hope that you would learn Scala just to use Hadoop. That was an unreasonable expectation. These days, almost most of its use is Python, but it still interfaces quite well with Java as well, because there's a lot of Java enterprise and business code sticking around. So these are all first-class citizens, well supported. Although there are interfaces to things like R. I'm sure at least a few of you out there are R people. Yes, R has interfaces too, but these are the official. Documents are all built around this. As we look at the documents and pull up the web browser with the official API documents today to use for exercises, you'll see it's got tabs to select any of these three languages. And it does lots of paradigms kind of built in, or the things we talked about, graph databases or machine learning or just SQL type accesses. They're all built in a kind of very friendly way. We don't have to cobble together accesses to them. But I would be remiss if I didn't point out that using Hadoop, the Hadoop file system, HDFS, as the backing store is very, very common. So the Hadoop file system is still very often the underlying behind the scenes file system that you might install to use with Spark. You might not. On bridges, we don't. On your laptop, for example, if you choose to install Spark and run it there, you probably won't. You'll just use its single drive. Why mess with that? But there are lots and lots of HDFS-backed Spark installations out there. So this is the idea. The idea and this is what you want to keep in mind as we start to use Spark here, is that we write these simple, nice, friendly programs in Python, Scalar, or Java here on the front end in what in Spark land's called the driver. You don't really have to worry about that. You're just writing what looks like a serial program. But as you run these serial programs, behind the scenes, behind a curtain right here that we're not going to peer behind very much, is all of your parallel computing machinery. That when you've installed Spark, if you've installed it on a big data center, it knows it's got all the stuff back here. If you install it on your laptop, maybe not so much. On Bridges, it knows dynamically what's behind the scenes, what it's got access to. So behind the curtain, it might have a lot of parallel disks and a lot of parallel computing power, so that whenever you do your search operations or other more sophisticated things like machine learning operations, it has all this parallel machinery. That's what makes this big data. We're going to do a lot of exercises here, and you might think, I could do that with pandas in Python. Yeah, but pandas in Python is not going to run in parallel automatically and scale up to use all of the cloud-based resources out there or whatever machine you happen to build in your department or have available to you. That's what Spark does. It scales up automatically behind the scenes. The secret to keeping it behind the scenes is that you have to store all of your data in what's called an RDD, a resilient distributed data set. It's just a data format that's very convenient. We'll stuff all of our data into it. It's very easy to get data in that format and work with it. As long as our data is in an RDD, it's going to automatically be able to use all this parallel stuff behind the scenes. If the data is not an RDD, if we're still using, like, say, regular Python variables and data structures, then we don't get any of this. So we want to make sure our data stays in RDDs. Again, it's easy to do. We'll find it's friendly to do, but it's something we do need to do. So here's the Spark formula. You load your data into an RDD. And for example, maybe that's a web visitor log. We've got a website and we want to see who's visiting our website all the time. And so we have an address log. Then we do transforms, what Spark calls transforms on the data. And transforms on the data are just kind of operations that do things like filter the data or turn it into something. Anytime you're massaging or manipulating your data, that's a transform. So we're going to do transforms on our data. Like in this case, we might want to filter out all the non-US visitors to our web log. So that's a transform. But here's one of the smart things that Spark does that makes it very efficient, is it won't actually do these transforms as soon as you type it in. It will wait. It'll do very lazy evaluation. It will wait until the last moment, till it's forced to squeeze out some data because you demand it with an action. Until then, we can keep loading up transforms. We can do more transforms on our data. Like, for example, we can say, we don't care about repeat visitors. We just want distinct IPs. So that's fine. It'll add these two transforms together, but not execute them yet. And you might say, well, what's the point of that? The point of that is that by combining all of your transforms at once, it can do things much more efficiently. It can minimize the data shuffling that has to go on between nodes behind the scenes and what can be kept in RAM and what doesn't fit into RAM. It can do a lot of very smart things. And so that makes it much more efficient. So this lazy evaluation is good. You don't really notice it so much as a user, but it's very useful optimization. Finally, as the user, though, you can actually demand the answer. You could say, with these here, you were just telling it, eventually I'm going to want something here, but you don't want it to spit back. So for example, when you do the transform, they filter out all the non-US IPs. That might be, so maybe you had 10 million visitors to your log, and all the non-US visitors leaves you with 8 million. Well, you don't want 8 million visitors back on your terminal screen. So these transforms are all, again, piling up in the background until you finally say, I want the data at my fingertips, squeeze it out. That action is something that returns data. Now Spark will go ahead and execute all these piled up transforms. So for example, you might say, give me the actual count of how many unique US visitors. Now I do want that number to pop back on my terminal. I do want it to say you had 4,000,002 unique US visitors. So that's the answer at the end of this. So this is how Spark works. And we'll do plenty of examples here, but that's the prototype. So here's a very, very simple example. Is we have a data set out there sitting on called it's a NASA's log of visitors to their website here, or accesses to the website. So let's keep track of what got accessed on their website. So instead of visitors, this is what got access there. First thing we want to do is read it into an RDD. So that's the number one thing, is get all of our data into RDDs. That's where we operate on it. So in Spark, a very simple command that you'll find very often to say read a text file in an RDD is this, text file. And it will just go out, find a text file, and read it into an RDD. And Spark's reading commands are very smart. It can support all kinds of formats. We'll show you some examples later. It can read zip files. It can read databases, whole database formats. So you can have a whole Mongo database sitting there, and it can suck it into an RDD and do all the translation and parsing for you. It's a very powerful and useful part of Spark. In our case, it just reads in this tab separated human readable file, just a bunch of lines of text, and it reads it into an RDD. Now, in all of my examples, I try to call them _ RDD. That's just me trying to be nice for this class. In normal Spark code, people don't call everything _ RDD. So get used to not having that crutch. But it's usually obvious from the context when something's an RDD. I just want to make it extra obvious for this class. Now, the Spark, you might say, okay, well, where are we starting with here? How is it, what's this Spark context thing that it's reading with right here? The Spark context is something that appears magically for us whenever we start up our Spark shell that we'll use to do our exercises. And it basically is just lets the Spark system know what hardware to actually look for behind the scenes. This is all the behind the scenes parallel hardware is all the Spark context. So when somebody installed Spark, that's not you today, that's some system administrator, might be you when you build it on your laptop, might be you if you're responsible for building it back in your chemistry department, but whoever builds the Spark thing says, okay, here's all the parallel computing disks and hardware that you have available to you, and that's the Spark context. So when you're a programmer or a user like we are, and it starts up, the Spark context is everything that Spark needs to know about behind the scenes. We don't have to worry about it as programmers, it's just magically there. If you go to run these as scripts, instead of separate independent programs, instead of we're going to do it from command line interactively in the shell, because that's neat and a fun way to analyze data is interactively. But if you want to run these as separate programs, you need to add a couple lines on the beginning of our examples to make them work, to make them know what the Spark context is. So these are a couple lines you stick on the beginning of all of our examples, and now these are standalone programs that can run. You could set them up to run automatically at midnight and send the CEO your sales data or whatever. We won't need them because we're going to do everything interactively here. Okay, so here we go. Did I hear, Steve, did you have a question? No? Okay. So here we go. We've loaded the RDD in.
Now I have a question, sorry. What if we have existing big data that was not created as RDD? Is it inexpensive to transform the data so that it can be analyzed via Spark?
Okay, well, that's a fair enough question. The question is basically, what if we have data that's not an RDD? Well, that's the normal case. The normal case is I don't expect any of our data is RDDs. This certainly isn't an RDD coming in. This is just a text file sitting on disk. So Spark programs, you start out assuming nothing is an RDD. Everything is sitting on disk somewhere in some other format. So nothing is an RDD. And when your programs start, they do translate things into RDDs. Now, this may or may not be expensive, but it's unavoidable, but it's usually very efficient because all these connectors to read files and whatnot are very, very efficient. So this data could be starting out here. As I said, it could be an entire database, Mongo database file. It could be a binary file. Spark's happy with many, many different data formats. And once it sucks it into an RDD, we're good to go. But the idea is the beginning of a Spark program is doing exactly that, taking data that's not Spark, that's not an RDD, turning it into an RDD, and then running from there. So don't assume that data, when you're in Spark, your data isn't typically sitting on disk as Spark data. It's sitting on disk in its native natural format. And when your Spark programs start up, the first thing they do is start reading that data in and on the fly converting it into RDDs so they can manipulate it. And when we're done and we do our analysis, we'll spit something out in a format that's not an RDD. Its final analysis might be a human readable text file, or just in our case, some information back to our screen. So this first thing of reading things into RDDs is almost every Spark program because your data doesn't live in a Spark format. Okay, in our case, we read in this text file. And again, this is human readable text file. All the files we'll use for our Spark examples, and as we get more and more sophisticated, they're going to be human readable text files. So you can go and just look at them with your editor and see what's up. But then we start doing our transform. So we're going to do our first transform on it. We're going to find all of our, we're only going to be interested in the people that were looking for links related to Stanford. So we're going to do a filter. This is going to be one of our first transforms here. A filter that, as the name suggests, filters our data down. It takes our data and only returns data that meet a certain criterion. And that criterion is defined for us by some function that we can write ourselves. It's a true or false function. So a filter says, give me a true or false function. And the true or false function that we're going to use here is one that's so simple, I didn't feel like writing a whole separate function for it. So we're going to use a lambda. So for those of you that are Spark or Python programmers, I hope you know what a lambda is. For those of you actually that are Java programmers, these days you should know what a lambda is. So for many of you that are programmers, you know what a lambda is. For those of you that aren't, I'll take a moment to explain it. A Lambda is a standard programming feature. It's not Spark related. It's just standard programming language that says it's an anonymous function, a function that's so simple typically that it's not worth writing a separate function for it. So Spark says this could be a separate function. Our filtering criteria might be really complicated. Maybe we say we want it to be Stanford, but only from certain years and only if it's related to certain user time. We can have a really complicated mess in here if we wanted to. And so we could write a whole separate function somewhere else and it could do this filtering. But many times, most of the time for us, we're going to find that our filtering function is so simple. I don't want to go write a whole separate Python program that just says is Stanford in line, because this is just standard Python. Stanford in line. It says is the string Stanford in line. So I don't want to write a whole separate program for that. So I use a Lambda. So Lambda is basically a shorthand function that says this is the argument that's being given to you. This is the program that runs on it, and it's true or false because it's filtered. So we're going to use lots of Lambdas here because it just makes sense. Anywhere you have a Lambda, we could have a much more complicated function if it made sense. Okay, so we do our filter, that's our transform. And then I want to find the answer. How many of these lines had Stanford in it? So I do an action, which is a count. And we'll get a list of transforms and actions on the next slide. But count happens to be one of the useful actions. It gives me the count. How many things are there in this RDD? And so when I do that action, then it spits out the answer. There are 47. And I might also do another action, which is show me the first element of that RDD. RDD is a bunch of elements, a pile of elements. Show me the first one. That's a useful thing to do. Here's the first one. And if it's a big mess here, that's just because this is a web server string. This has nothing to do with Spark being messy or anything else. It's just a big web server string. It's a Unicode string. That's what this U means here, because Spark by default uses Unicode strings. It's a Unicode string, and this is what that looks like in a web server log of accesses. So it's nothing. This don't bother trying to read this cryptic bunch of nonsense. It's just at the end of the day, it's just a GIF file that sits here. So this is a walkthrough right here of exactly what Spark can do. We're going to do some more complicated examples, but first, let's look at the most common transformations and actions that we have at our fingertips. So here are the common transformations that we're going to find ourselves using. And there's a full list here. There's lots and lots more finely tuned and useful ones. And you'll find as you have this web page open next to you, I recommend it as you do the exercises, you'll find lots of other transforms, but these are the ones that are by far most useful. Filter we just looked at. Filter basically says distill the data down. Take an RDD and only give me back elements which meet some criteria based on some simple function. So this gives us few elements back. Sometimes we want to take our RDD and instead transform it into something. Maybe we want to get rid of all the capital letters because we're going to do text translation. So we want to take all of our words that are in there and translate them all to lowercase. That's a transform that has the same number of elements come back. That's map. So map is very useful. The third very useful one, and sometimes confuses people a little bit, is what's called flat map. Flat map is one that returns more elements than it's given. And the canonical case here, the one that everybody cites here, and the one that we'll find ourselves using, is that say that I give you a text file with a bunch of lines, and instead I want to break it up into words. So I might have read a text file with 1,000 lines, and instead I want to do a word analysis on it for my natural language processing. Well, I got 1,000 lines, but I want an RDD back that's words that might be 8,712 words. So I give it 1,000 RDD, I want 8,712 words back, so that's a flat map. So this is a function, in that case it would be the function that splits each line up into words. Python has a standard built-in command called split, for example. We might feed it as our function. So if we give flat map split and we give it an RDD of lines, it'll give us a bunch of words back, more elements. So these are three popular transformations. Some other ones, one we actually saw already in a little example, distinct. You might want to get rid of the redundant elements. That's a good transformation. Spark is used for real data processing, and so it's got lots and lots of sampling things built in capabilities because in real probability statistical analysis, sampling is important. So we got sample RDDs. We can combine RDDs with union. We can do intersections of RDDs. We can subtract them. We can get a Cartesian product, which is basically saying all combinations of two RDDs. And we can even create a little RDD on the fly right in the middle of our program. Instead of reading it in from a disk, we can just give it a list of items. We can just say, create an RDD out of this list of I've got a list A, B, C, 4, 5, 6, and it'll just make an RDD with those 6 elements right there on the fly. So these are some very popular transformations we'll find ourselves using. Now the actions that we'll find ourselves using, again, there's a longer list here. But the actions that are very popular are going to be collect. That gives us back all the elements and spits them out for us when we're done with analysis. And usually you want this at the very end, because in the world of big data, we're manipulating millions or billions of elements, right? And so you don't want to collect, you don't want spitting back to you billions of elements typically. You only want the final end result. Maybe you want the top 10 users out of 2 billion users. You know, you want the top 10. So you only do the collect when you finally got down to an RDD with 10 elements. So you only do collect on a reasonably small RDD. That's usually your final answer. However, you can do count at any time to see how many elements there are. So I can do count and go, oh, there's 2 million users. Well, I don't want to collect those. Let's start filtering them down. And I can do count, and I can say, oh, I filtered them down to the users from this one zip code that I'm interested in. How many are there? There's 12. Okay, now I can collect them. So count gives you the number. Feel free to do that at any point in time. Collect, you pretty much want to save till the end. We can do count by value, so we can look at any particular value in the RD, how many there are. And then we're going to find out a very, very useful thing that if you're new to this whole idea of data stuff or parallel computing or computing, might at first seem like it's only marginally useful, but we're going to find out it's incredibly useful, which is a reduce capability. Reduce is a function that says, how do I combine any two elements of my RDD? And based on that definition, if I keep applying that repeatedly to the elements, I'll come down to one final element. Okay, let me make that concrete for you so that makes some kind of sense. Why would I want to do that? Let's say we want the sum of all the elements. That's a reasonable thing to ask, right? I want the sum. I've got all these elements that represent, say, dollars that users spent. I want the total dollars spent by my users. I want the sum of all of these. Well, you could just say, I'm going to have a sum command, and it's that simple. And Spark has a sum command like that. But you can also say, I want to be able to define a command that combines things down myself, that takes any two elements, because it's going to be much more efficient if behind the scenes Spark does this in parallel, 2 by 2. Why does that make sense? Well, if I asked all of you out there, there are 400 of you out there today, if I ask all of you to sum up, you each have a number, you have your own number out there, and I want to sum. Well, I could either have each one of you in chat type in your sum, and I could start adding up, and it would take me 400 steps to add it up. I don't want to do that. Instead, I could tell each one of you to turn to your neighbor. While you're not in a classroom today, pretend you were in a classroom together. I could say, turn to your neighbor and add your sum. Now, in one step, I'm from 400 down to 200. Now I say, each one of you that has a remaining sum, turn to your neighbor and add your sum. Now we're down to 100. We'd find ourselves in 8 steps being able to do a sum and get our full answer in 8 steps instead of 400 steps. So being able to combine things in twos and filter them down in kind of like a tree, if you want to think of it that way, is really efficient. So we'll find ourselves using these reduce functions a lot. The most common ones you'll use are sum and minimum and maximum. These all work that same way. If there was a minimum amongst the 400 of you, want to find who had the smallest number. Okay, all of you turn to your neighbor. Whoever has the smallest number, keep it. Well, now we're down to 200, right? So the same idea. So reduces are very, very common and powerful and useful. So I hope you get comfortable with them before we're done with the workshop. We'll find ourselves using them a lot. Okay, some other actions. First, we might want to see the first one or the first 5 in an RDD. We'll do this a lot. So if you do have your RDD, it's got 2 million users in it still. Well, I don't want to look at all 2 million users, but I would like to make sure I got the right kind of data in there. I want to, as I'm doing my transforms, I think I just transformed from all of my users with the raw data, and now I'm just down to users and their address. Well, how do I check that? I don't want to do a collect and pull 2 million users back. But if I take the first 5, I can look and make sure at least I'm on the right page. So I'll take the first 5, and you'll find that to be very, very useful to do as a sanity check. I can look at the top users. I can take samples again. So there's a lot of transforms. These are the ones, though, that you'll find yourselves using a whole lot. Okay. We also have the notion of key value stores are quite useful. Key value stores in RDD land are very simple. Anytime we've got an RDD, the elements of which are made of 2 things, it's automatically a key value store. It treats the first thing as a key and the second as a value. So if we've got an RDD, it's got, say, 1,000 elements, but every one of those elements is just a pair of things. In Python, it happens to be a tuple. So if each one of those things is a pair of things, then automatically that is what's called a pair RDD, and it's a key value store. So if we look at my RDD and all of my elements are something like a name and a zip code, if that's what I've got, then that automatically is a key value store. I can treat it. It's also just an RDD with all the elements being 2 things. That's a fine way to think of it. but I also have some additional operations that work only on those kind of key value RDDs. And so let's look at some of those operations I can do. I could do reduce by key. I can boil down all the ones that share the same key into one thing. I can group by key. I can sort by key. So I can do things that are key value type operations if I know that all of my elements are just made of two pieces. And this is a common thing. So we'll find ourselves using that functionality almost immediately. And you still have all the regular transformations because, as I said, it's really just a regular RDD, except that all the elements have two pieces. They're all pairs. The interesting part becomes where we can start to do some special pair RDD actions like, well, not what we count by key and look up a key. That's nice. But we can also do some transformations that look an awful lot like classic database transformations. So for those of you that have any database experience, you know what joins are. Joins are a very common and important thing to do with databases. They show up all the time just doing what are normal operations. For those of you that are new to databases of any sort, which I'll assume are many of you out there, you might find this definition here of what they do. They take and combine all the elements with matching keys in the first RDD with the second RDD, and then they combine all the values in those keys together. They gather them together. This at first sounds like a really kind of odd thing. Why do I really want to do that, or how often am I going to do that? We're going to find ourselves doing this a whole lot. Joins are very popular. There are even variations of joins that are also important. But this straight up join here, inner join, is going to be it's going to be very important to do because it is a way to take two RDDs and combine their data together that's going to pop up in all kinds of applications. We're going to find ourselves using this just naturally in normal type of operation. Again, database people out there are like, of course, joins happen all the time. Otherwise, if you're new to this, well, be prepared to be impressed by how often you want to do this particular operation. When we do it, it'll explain itself more. So I'm not going to make us pick through this without examples. We'll have some examples. As a matter of fact, I have an example on the very next slide, which is this one. So we have a database of our top purchasing customers. These are our best customers. And so we make our own little RDD right here. We can create an RDD on the fly. That's what this parallelizes. I didn't read this from disk. I'm going to create it right here on the fly. I'm going to make an RDD. And it says, Joe spent $103, Alice spent $2,000, Bob spent $1,200. Now we have customer addresses. So we're going to create our own little RDD of addresses on the fly too. So this gives Joe an address and Frank an address. These are both pair RDDs. They're just regular RDDs, but if we look at them, we notice everything here is a key and a value. So this makes them a pair RDD, which means what if I want to create a mailer for my top purchasing customers? That means I want to take this RDD, which has their spending information, this RDD, which has their address information. I want to combine them together. But I only want the common keys from this first RDD. So Joe is in both of these. So I want Joe to come out the end here, and I want Joe's address and how much he spent. And Alice is here, but Frank's not one of my best customers. I don't want Frank appearing in my output. So we're going to find out that the operation defined by join on that previous page is exactly what we want. It's going to combine these two RDDs to make sure that our promotion mailing RDD is just the customers. So here we are, just the customers that were in both RDDs with their keys, and it combines the values from both of them. So here's the information I want. So that's not too weird of a search to do, right? This makes sense. And the join was the answer. So we'll find ourselves using these joins as we go along. Okay, we're going to do our first exercise here based on, and we're right on time here. Do our first exercise is going to let us test some of these capabilities. And we're going to do a little data analytics. Data analytics is a simple way to get into the much more interesting world of natural language processing, which is very important. Sentiment analysis, for example, on tweets, on Facebook entries and things to allow people to see what's trending is not only lucrative in the consumer world, but at the moment, for example, to put something in a very timely sense, at the moment, there are a number of groups that are attempting to analyze COVID spread by looking at analyzing people's tweets and their posts on social media to see if people asking about, I have a cough, I have certain words, keywords. And if you can do it in a sophisticated manner, right? If you just say who's mentioning cough, right? That could be everybody. But if we can start to do sophisticated text analysis on tweets or other mineable sources of data, maybe we can get ahead of where things are about to break out. We can see symptoms. Oh, people in this area, when people start talking about coughs in conjunction with headache or whatever, this is turning out to be where we're going to have an outbreak, or testing is going to correlate strongly with it. Things like that. turn out to be very useful and quite effective. So this is a good introduction to that kind of analysis. We're going to take a look, and this is something that people actually do on its own sake, which is Shakespeare. People have been analyzing Shakespeare for forever, but these days with big data, they can start to do subtle analyses of his text, and people question whether, for example, Shakespeare actually authored all the plays, or perhaps it was Marlowe. And so you can do text analysis on Shakespeare, and we're going to do a little bit of that ourselves in a fairly simple way. Now, as we do this, I want you to keep in mind.
I have a question.
Question, yes.
Does the loaded text file have to have structured format to use Spark? sc.textfile command. Can it be unstructured, e.g. different number and kind of entries in columns, rows?
Oh, that's a very good question. Okay. So does the file that we read in with text file have any structure? With text file is a very simple, of the many options we have available to read into an RDD, text file is very simple. It reads in, each line becomes an RDD element. So that's all the structure text file is going to give you, and that's by design, and that's fine because that's as much as it's meant to do. So any file you read in, so if you have, let's say we have stuff that's got lots of columns, we're trying to read in, I say it's a nice human readable format file, but it's got a lot of columns. Say it's actually a table, and we want to read it as a table. Text file will read it in line by line. That's probably not what we want. However, we can easily, and we'll see this a little bit later on, we can easily, with data frames, read in that text file as an actual table, and we can preserve the column structure of that data and the fields. So text file is not the answer to our problem, but we'll see with data frames at the end of this lecture, actually, we'll see with data frames that we can read in things with table structure to them. And we can even read in actual binary formatted database files and whatnot. But so text file, no, is not the answer. If you've got structure in your table type structure, for example, text file is not the answer. Text file is the answer, though, if we want to read a bunch of lines of text. So no, we're going to, text file, just each line is an element. That's as far as it goes. Say, for example, like I said, a nice table, we can read that in with data frames, and it'll read it in and keep the data format. We'll have fields, and it'll be nice and preserve all that, and be one command as well. So, but at the moment, text files are our only tool, and it just reads in one line per element. Okay, so in our case, that's going to be good enough because our text file that we're given to us of Shakespeare is the lines of all the complete works of Shakespeare. So it's just a bunch of lines of text. And when we read it in with text file, it'll just read it in as a bunch of lines of text. So for our immediate purpose, that's fine. But as we do this, I want you to keep in mind, many of you may be out there that have some experience, might say, okay, I have ways to do this. I can do this with pandas or some other NLP, toolkit stuff that I have sitting around in Python. And that is true. There are many ways, because Shakespeare is small enough. It's only, 500K or something. Shakespeare is small enough that you can do this with lots of simple, just laptop-based Python tools. That's not the point. The point of this, I want to give you a small enough exercise that's manageable, that we can all read the file and move it around easily, and it runs in fractions of a second. But this scales up. What we're learning here with Spark will scale up to read not just the complete works of Shakespeare, but to go through Library of Congress size data sets and plow through those in reasonable amounts of time. So please don't, as you look at Spark and you think of all the other ways, because many of you will say, I could even write I could write a few lines of Python code to just do this or whatever, or I know of some other way. Bear in mind that the other ways you know of to do this are not going to scale up and work on a cloud in a data center automatically, like Spark will. Everything we're going to do here will scale up. So yes, pandas will work here too, to go through the works of William Shakespeare. It's your single librarian. But Spark will go through the whole Library of Congress with an army of librarians. So there's a difference. So keep that in mind as you do what are reasonably small exercises for your sake. I didn't want to give everybody a petabyte database to scale through, because it would take you minutes or more to do each exercise. Okay, so here's our problems that we're going to do. And we're going to give ourselves about 40 minutes, maybe a little bit more. I'll kind of get a sense of the questions. Let's say 45 minutes. And before anybody panics, I realize our first break is coming up. That's intentional. So we have an hour break here. This is not meant to be your exercise time. After we come back from the break, we will take 40 minutes of exercise time. Those of you that, because of your schedule today or whatever, want to use the break to do exercises, go for it. Those of you that actually intended to go get lunch, do whatever you want to do, please, that break is yours. That's not the 40 minutes I'm talking about. But we're going to give ourselves about 40 minutes. Like I said, maybe a little bit more if people need it. We'll get a feel for it. to work on this exercise. So here's our exercise, is we've got this input file, and you can also find this whole database at gutenberg.org. It's just a nice human readable text file. And we're going to read it in. So it's this, I'm giving you the first line of the exercise. Oh, by the way, here's what you need to do to actually, in case you haven't so far, to get going from scratch. Once you're logged in, you type interact to get an interact node. You go to your Big Data Shakespeare directory. CD is the command in Unix to change directories. Make sure you load the Spark module, because if you don't, the PySpark command you type next won't work. If you load the Spark module, when you type PySpark, you will find that it starts you up automatically in a nice Python-looking shell. So it just looks like an IPython shell. If you're a Python programmer, I hope you're comfortable there. If you're not a Python programmer, there isn't a whole lot there that you'll need to suss out. There's a little bit of command history with the up arrow or backspace. You can kind of go back to previous commands. Some simple editing stuff, but basically it's a nice interactive shell. And by the way, that's pretty neat in that one of the things Sparks gives us is the ability to, with larger data sets, with things that are actually substantial, with your terabyte-sized data sets, we can interactively play with the data if we've got a real serious Spark machine behind it. We can do interactive analyses that on your laptop might take you 15 minutes, if it can even fit, to analyze. And on a Spark setup on a real machine, it might take 5 seconds. That's a totally different way of working. Now we can interactively mine our data, play with the data. Whereas if you got to wait 15 minutes between everything, you don't get to play with the data so much. That's a neat aspect of Spark, but with our Shakespeare exercise, it might not be so obvious. So we're going to do a few simple things here. We're going to count the number of lines. I hope it's pretty obvious at this point in time how you might do that. Count the number of words. And if you're a Python person, I'm sure you've seen split before. That basically splits lines into words. If you're new to Python, split is a Python function that is very popular because it splits a string into individual words. We want to count the number of unique words. So these first 3 are pretty straightforward. These next 2 are going to be a little bit more challenging, and they could be very challenging if you're completely new to this, and I'm assuming that a fair number of you are. If any of you are previous database people and you are comfortable with the ideas of key values or whatever, you can probably pick your way through this pretty directly. But if you're new to this, these last 2 are going to be challenging. Don't get frustrated with it. Normally in a class environment, we have the wide area classroom. People can kind of work in teams and give each other hints and help. I regret that with the Zoom only, we don't have that. I think it'll probably make this a little bit more challenging than I'd like. I really like to see that social interaction of people helping each other. We won't have that directly here, unless those of you are sophisticated and are setting up your own chat channels and whatnot out there. But I'm going to assume you're on your own, in which case you might find these a little bit challenging, but give them your best shot. And these last 2 are to count the occurrence of each word. So get the word frequency of each word and then show me the top 5. So at the end of this whole pipeline here, what are the 5 most frequently used words in the works of Shakespeare? And I might expect that there are going to be some pretty boring words like and the, but give me their counts and show me how frequently they're used. Now, these last 2, I'll give you a little bit of a hint. One thing, at least one approach, is to think key value. And the reason that hint is maybe more obvious to people that do a lot of database stuff is that the thing I'm asking you at the end of the day to give me, the 5 most frequent words, right, is going to be something like and then it's word count. So it showed up 25,000 times. The showed up 23,000 times. Well, to an experienced data scientist, seeing that right away, that's a key value. I got a key and a value. I got 2 things. Right away, they get the idea that at the end of the day, I'm getting a key value out of this data. So that's something that it's not at all obvious. Don't feel bad if you're new to this. It's not at all obvious that that's key value. But to a data scientist, that looks like a key value. They get that they're going for a key value at the end. Another thing is along the way, you might find yourself wishing that the key was the value and the value was the key. That's another very common thing when you're working with key value type data. And if that's the case, well, then make that happen. Don't think, oops, I hit a dead end, or no, think, okay, I wish the key were the value. Well, flip them. So that's one, these are some leading hints to give you one approach that might work for you. But again, this is going to be a little bit more challenging, but it's worth working through. And of course, we'll go over the answers. So give it your best shot. So we're coming up on the top of the hour. And again, I'm respecting your break time here. I'm not assuming this is exercise time. Feel free to use it. I will disappear myself for the break. On all of our exercise sessions, I will be here and the TAs will be here to answer your questions. So please, during the exercise sessions, don't hesitate to ask questions, and we're happy to see them. During the actual break today and tomorrow, I am going to actually take a little bit of a break. So I won't be here for the entire break. I'll probably be back for most of it, to be honest, but don't count on it. So I will actually disappear in a few minutes, and I will come back and answer your questions as I can. But at the top of the hour, so that's 2 o'clock Eastern time, I will be back, and we will be full time during the exercise session today and all other exercise sessions here to answer your questions during the exercise session. So we're here for the exercise sessions. We may not be here for the breaks. And so at the top of the hour at 2 o'clock Eastern time, you have 40 minutes starting then to work on the exercise. Get a jump on it if you'd like. Otherwise, I will be back here just to say hi at the top of the hour, and we'll give ourselves 40 minutes to work on the exercise. Okay, with that, I will probably see if there are some pending questions here and help out a little bit before I do disappear and get myself a little bit of energy over the break. So please work on exercises, enjoy a sandwich, do whatever you'd like, and we'll see you all back here at the top of the hour to exercise time.